far beyond the stars familiar in our night sky. In a quiet area of the constellation Leo, a faint shift in infrared light reached Earth after journeying more than a century through space's darkness. At first glance, it appeared like just another data set, one more number stream among trillions gathered by humanity's most potent telescope. But concealed inside that light was something no one anticipated. A chemical mark that does not belong to rocks, oceans, or storms, but to life itself. The James Webb Space Telescope had just identified a world so perfectly equilibrated, so chemically vibrant that scientists attained a certainty level rarely observed in astronomy. Not a maybe, not a possibility, but a planet that seems fully habitable and potentially more life-friendly than Earth. What Webb has discovered doesn't just imply life might exist out there somewhere. It implies we may have finally located it. The breakthrough came quietly, embedded deep within infrared data, gathered as a distant planet transited its star. As the starlight passed through the planet's atmosphere, certain wavelengths were absorbed, creating a spectral imprint. At first, scientists spotted familiar compounds: water vapor, methane, carbon dioxide. Each one significant, each one indicative. But then emerged the molecule that altered everything: dimethyl sulfide. On Earth, this substance is generated only by living beings, not volcanoes, not lightning, not mere chemistry life. And the signal was not faint. It was robust enough that the chance of error fell below 3 in 1,000. In a discipline where doubt is standard, this confidence degree is remarkable. The planet called K2-18b circles a red dwarf star 120 light-years distant, squarely within the zone where liquid water can persist. But unlike the rocky Earth-like world scientists once thought essential to discover, this planet fits a completely different category. A super-Earth, bigger, denser, enveloped in a thick hydrogen-rich atmosphere. And rather than rendering it inhospitable, that atmosphere might be precisely what renders it perfect for life. K2-18b is not teetering on a knife's edge like Earth. Its setting seems extraordinarily steady. The planet's surface heat lingers around 120 degrees Fahrenheit, warm enough for liquid water, yet mild enough to keep oceans from evaporating. This heat is not coincidental. The hydrogen-rich atmosphere functions like a global blanket, capturing warmth and spreading it uniformly across the world. Unlike Earth, where heat varies between day and night, summer and winter, this planet may undergo consistent conditions planet-wide. Even the night side, trapped in eternal shadow from tidal locking, stays warm enough to support liquid water. Gravity holds a vital part here. With almost 3 times Earth's surface pull, the planet grips its atmosphere effortlessly, stopping it from leaking into space as Mars did eons ago. What appears extreme to us could actually be a benefit. Intense gravity, dense atmosphere, stable heats. Together, they form an environment where life does not have to battle endlessly for existence, but can instead concentrate on expansion, intricacy, and development over vast durations. The star sheltering this planet is a red dwarf, tinier and cooler than our sun, but much more lasting. While our sun will one day swell and wipe out all life on Earth, red dwarfs glow steadily for trillions of years. That means any life arising on a world like K2-18b has nearly endless time to develop. The planet finishes an orbit every 33 days, positioned near its star, yet absorbing almost the same energy per square meter that Earth gets from the sun. This locates it firmly in the habitable zone, but with one key distinction. The habitable zone near red dwarfs endures far longer than around stars like ours. Combine that with the planet's thick atmosphere, which protects the surface from damaging rays and reallocates heat worldwide, and you start to understand why scientists are reevaluating all they assumed about habitability. This finding indicates that Earth-like planets may not be the top spots to seek life after all. Instead, the universe might prefer worlds that are larger, warmer, and much more stable than ours. What really elevates this finding is not merely the planet's position or heat, but the conduct of its atmosphere. The identified gases reside in a condition of chemical imbalance. In a barren world, these compounds would interact and vanish. Yet, they endure in substantial amounts. On Earth, this sort of atmospheric disequilibrium is sustained only by biological processes. Life continually injects gases into the air, blocking it from achieving chemical balance. K2-18b displays the same design. The lack of ammonia, a substance anticipated in lifeless hydrogen-rich worlds, bolsters this argument even more. Something seems to be actively eliminating it, something alive. If this view endures, then we are not viewing a planet where life might arise someday. We are viewing a planet where life is already molding the setting on a worldwide scale. A living world respiring across interstellar distances detectable from 120 light-years away. For decades, the quest for life beyond Earth adhered to a strict template. Scientists thought that to locate life, they needed to find a planet nearly identical to Earth. Similar dimensions, similar weight, a slim atmosphere, a rocky exterior, a sun-like star. K2-18b demolished that whole structure in one discovery. This planet is not Earth's duplicate. It is Earth's odd, oversized relative, functioning under principles we once deemed hostile to life. With a mass over 8 times Earth's, K2-18b fits a group of planets called super-Earths. Worlds once rejected as swollen, unlivable, gas-laden forms unable to maintain biology. Yet, the data narrates a vastly different tale. The planet's huge gravity serves as a benefit instead of a burden, securing its atmosphere solidly and averting the gradual atmospheric decay that condemned Mars. Its dense hydrogen layer, once considered incompatible with life, instead forms a stable thermal setting that safeguards liquid water throughout the planet. This finding compels a deep change in outlook. Habitability is no longer about delicacy and ideal equilibrium. It may be about toughness, bulk, and enduring stability. K2-18b implies that the most life-friendly worlds in the galaxy are not fragile replicas of Earth, but sturdy planets constructed to last for trillions of years. Beneath K2-18b's hydrogen-rich heavens lies what could be one of the most remarkable settings ever uncovered. Vast worldwide oceans, possibly hundreds of miles deep, made of water blended with dissolved hydrogen under massive pressure. This is not an Earth-like sea limited to shallow depressions and continental edges. This is a planetary sea, a globe-encompassing liquid setting that overshadows every ocean in our solar system together. The existence of hydrogen basically alters how this ocean operates. Hydrogen mixed in water broadens the span of heats and pressures where liquid water can persist, permitting stability far past Earth's boundaries. On our planet, extreme pressure crushes biological forms. On K2-18b, hydrogen serves as a natural cushion, preserving conditions fit for chemistry and possibly biology, even at astonishing depths. This unlocks the potential for ecosystems of inconceivable magnitude. Life would not be restricted to shorelines or surface waters. Whole biospheres might exist stratified through the depths, flourishing in warm, chemically abundant settings where energy supplies are plentiful and steady. In such a sea, evolution would not be hindered by shortage. It would be hastened by plenty. The most disturbing ramification of Webb's readings is the pure intensity of the biosignatures identified. Dimethyl sulfide is not a compound that persists quietly in minute quantities. It degrades swiftly under stellar rays. On Earth, its ongoing presence in the air demands constant renewal by living beings, mainly across extensive oceanic areas. For Webb to identify dimethyl sulfide from 120 light-years distant, biological activity on K2-18b cannot be confined or minor. It must be global. This is not a world where life grips isolated havens. It is a world where life commands atmospheric chemistry. The levels detected suggest a biosphere functioning at a scale far exceeding anything humanity has known. Whole oceans respiring, metabolizing, and remolding their planet's air without cease. This is not the soft murmur of microbial endurance. It is the thunder of a prosperous planetary ecosystem. The atmosphere itself turns into a living mechanism trapped in chemical disequilibrium because biology is actively stopping it from falling in a lifeless balance. K2-18b does not simply shelter life. It is molded by it. The ramifications of K2-18b stretch far past one planet. Red dwarf stars like its host compose about 3/4 of all stars in the Milky Way. If even a portion of the planets circling these stars mimic K2-18b, then the count of potentially habitable worlds in our galaxy rises not by a factor of 2 or 10, but by hundreds. Worlds once dismissed as too bulky, too hydrogen-laden, too foreign, are abruptly reclassified as leading prospect for life. The universe may not be thinly dotted with rare, Earth-like havens. It may be thickly packed with super-Earth water worlds, each cloaked in dense atmospheres, each stable for trillions of years, each able to host biospheres that ripen far past Earth's present phase. The uncovering of K2-18b compels a drastic conclusion. Life may not be the anomaly in the universe. It may be the standard result wherever physics permits stability, water, and time. And the James Webb Space Telescope has just offered humanity its initial clear view into that truth. For years, hydrogen-rich atmospheres were viewed as an impasse in the hunt for life. Hydrogen was considered too light, too reactive, too unstable. On Earth, it flees into space nearly as soon as it emerges. On K2-18b, hydrogen does the reverse. It rules the atmosphere, forming a thick, massive layer that redefines the whole planet's climate and chemistry. This atmosphere does not simply rest above the surface. It actively joins in controlling heat, pressure, and radiation levels across the planet. By capturing infrared warmth with exceptional efficiency, it erases extreme temperature differences, avoiding the fierce climate shifts that test life on Earth. Day and night merge into a continual habitable condition. Seasons become meaningless. The planet does not swing between endurance and ease. It stays easy relentlessly. So in this setting, biological systems are not endlessly compelled to adjust to strain. Instead, they are liberated to refine, to expand bigger, to branch out, to test intricacy. The hydrogen atmosphere, once deemed hostile, arises as the ultimate stabilizer, converting K2-18b into a planetary nursery crafted not for survival, but for thriving life. The chemistry of K2-18b's atmosphere narrates a tale that extends far beyond mere habitability. Methane, carbon dioxide, water vapor, and dimethyl sulfide coexist in mixes that should not endure. In a barren atmosphere, these compounds would react, neutralize, and achieve balance. That balance never comes. Something is endlessly injecting energy and substance back into the mechanism. On Earth, this function is fulfilled by biology. Forests, oceans, microbes, and ecosystems ceaselessly circulate gases through the air, blocking chemical stagnation. K2-18b exhibits the same mark, but on a magnitude that dwarfs Earth. The levels identified imply not just biological existence, but biological supremacy. Life is not a rider on this planet. It is the motor. The atmosphere acts less like a fixed casing and more like a metabolic tool handling chemicals in real time as a planetary scale biosphere respires below it. Every transit seen by Webb strengthens this image. This is not a planet awaiting life start. This is a planet where life has already seized command of its setting and remolded it into a self-maintaining system. Perhaps the most overlooked element in the rise of complex life is time. Earth has lasted for roughly 4.5 billion years. Yet complex multicellular life surfaced only in the closing portion of that record. K2-18b resides in a fundamentally different temporal setting. Its red dwarf star will glow steadily for trillions of years. Not billions, That means the planet's habitable states are not temporary. They are virtually eternal on cosmic scales. Evolution on K2-18b is not hurrying against obliteration. It is progressing at ease. With steady heats, a lasting atmosphere, immense oceans, and near-infinite time, life can investigate evolutionary routes that Earth-based life never got the opportunity to try. Complexity is no longer limited by disastrous restarts. There is no impending stellar demise, no unavoidable runaway greenhouse, no countdown. In such a setting, biological systems could become unimaginably elaborate, possibly forming layered ecosystems that cover oceans, atmospheres, and chemical slopes we scarcely comprehend. K2-18b is not just habitable now. It may have been habitable for billions of years already, and it may stay so long after Earth vanishes. The identification of K2-18b signifies a pivotal moment in human history, not because it resolves every query, but because it alters the query itself. For generations, humanity wondered if life might persist elsewhere. Webb's data redefines that query completely. The fresh query becomes how prevalent life truly is. If a planet so dissimilar to Earth can shelter a flourishing biosphere, then the galaxy's tally of living worlds grows massively. The Milky Way is packed with red dwarfs. It is packed with super-Earths. It is packed with hydrogen-rich planets that were once overlooked. K2-18b implies that life does not demand a limited array of Earth-like states. It demands stability, chemistry, water, and time. And those components seem plentiful. Webb has not simply identified a habitable planet. It has revealed a universe that may be tuned for life in ways we never expected. A universe where Earth is not the model, but the outlier. A universe where life is not scarce, delicate, or brief, but enduring, versatile, and extensive. One of the most extreme notions to arise from the data is that life on K2-18b may not persist despite its setting, but because of it. On Earth, life endlessly fights instability, heat swings, ice ages, asteroid strikes, volcanic winters, atmospheric depletion. Evolution here is formed by turmoil. On K2-18b, the setting seems to do the reverse. It cooperates. The hydrogen-rich atmosphere does not merely shield the surface from rays and heat loss. It forms a chemically lively medium where energy is simple to obtain and spread. Hydrogen is not just an atmospheric part. It is fuel. It can be metabolized. It can join chemical loops that supply energy without sunlight. This unlocks the potential for biospheres not reliant on photosynthesis alone. Whole ecosystems might persist separate from the star, pulling energy straight from chemical slopes in the atmosphere and ocean. In such a world, life is not limited to narrow ecological slots. It expands. It occupies every open layer of the planet from the upper air to the deepest sea depths. The setting does not menace extinction. It hastens intricacy. Evolution is not merely about mutation and choice. It is about length. On Earth, complex life arose late and stays vulnerable. K2-18b exists under conditions that permit evolution to complete its path. Billions of years without disastrous restarts. Trillions of years yet to come. This is not an evolutionary test abbreviated. This is a finished procedure, or at least one much more advanced than Earth's. If life started early on K2-18b, and there is no proof indicating it could not have, then that life has had more time to develop intricacy than life on Earth has ever possessed. Multicellular beings, planet-scale ecosystems, chemical loops honed over ages. The biosignatures identified by Webb may not signify primitive life at all. They may be the residues of a profoundly evolved biosphere functioning at peak efficiency. We are not necessarily viewing life start. We may be observing its balanced state, a biological mechanism so refined that it has completely merged with its planet's atmosphere, oceans, and chemistry. For generations, Earth-like meant rocky, temperate, oxygen-rich, known. K2-18b compels a redefinition. Earth-like may not mean akin look. It may mean akin results. Steady heats, lasting liquid water, enduring atmospheric hold, active chemistry sustained by biology. By those standards, K2-18b may be more Earth-like than Earth itself. Our planet rests on the brink of multiple breakdown modes. Runaway greenhouse impacts, atmospheric decay, stellar development that ensures eventual ruin. K2-18b, in contrast, seems crafted by physics for longevity. Dense atmosphere, strong pull, stable star, massive seas. Is a world built to endure. In this fresh structure, Earth starts to appear like a delicate exception, while planets like K2-18b arise as the prevailing type of habitable world in the galaxy. The ramification is disturbing. If Earth is not the norm, then most life in the universe may persist in forms and settings profoundly foreign to our understanding. Until now, the hunt for life beyond Earth has relied on deduction, indirect proof, likelihood debates, statistical frameworks. K2-18b signifies the first occasion those concepts start to solidify into something concrete. A planet with water, with stable heats, with atmospheric chemistry that should not persist without life, with statistical assurance nearing certainty. This is no longer a theoretical debate about whether life could exist elsewhere. It is a scientific probe into where it already does. The James Webb Space Telescope did not simply identify a habitable planet. It proved that we now hold the instruments to recognize living worlds across interstellar spans. The ramifications spread outward. If one such planet can be located so distinctly, then others will ensue. This finding is not a conclusion. It is a demonstration of ability. Humanity has passed a boundary. We are no longer guessing about life in the universe. We're starting to inventory it. One of the most alarming ramifications of K2-18b is how smoothly it appears to sustain life. On Earth, habitability seems accidental, almost unstable, as if life passed through a narrow cosmic gap that could have shut any time. On K2-18b, the states seem reversed. Habitability is not a delicate equilibrium. It is the natural result of the planet's build. The dense atmosphere evens out extremes. The gravity secures everything firmly. The oceans endure without vaporizing or solidifying. The chemistry stays lively without falling into balance. Nothing about this world implies that life is endlessly on extinction's edge. Instead, the planet acts like a mechanism that anticipates life to exist, as if the physics itself is adjusted to maintain biological processes running endlessly. This redefines life not as a scarce wonder, but as a foreseeable outcome when sufficient stability, energy, and chemistry are permitted to coexist long enough. K2-18b does not appear like a fortunate anomaly. It appears like a model. When scientists envision alien life, they often imagine beings clinging to a planet's surface, exposed to its star and air. K2-18b implies something much more vast. With oceans possibly hundreds of miles deep, blended with hydrogen, and kept at stable heats, life would not be limited to a slim surface stratum. Whole ecosystems could persist vertically, arranged through pressure slopes, chemical strata, and heat zones. Some beings might flourish near the surface, engaging with the air. Others could dwell far beneath, nourishing on chemical energy freed from the planet's core or from reactions in the hydrogen-rich sea itself. This generates the chance of a biosphere that is not two-dimensional but volumetric, a living planet in 3 dimensions. The biosignatures identified by Webb may be the atmospheric resonances of these deep, hidden ecosystems gradually spreading upward until they etch themselves on starlight. What we are identifying may be only the outflow of a much vaster concealed biological engine working below the clouds. Perhaps the most disturbing notion is this. K2-18b may not signify the start of extraterrestrial life, but an advanced phase in a narrative that began long before Earth even shaped. Red dwarf stars light up early and endure nearly eternally. Super-Earths develop swiftly and keep their atmospheres effectively. If life arose on K2-18b billions of years prior to emerging on Earth, then what Webb is identifying now could be the atmospheric mark of a biosphere that has already traversed evolutionary phases we have not yet attained. This does not demand intelligence. It demands time, and K2-18b has possessed more of it than Earth ever will. In that setting, humanity is not uncovering life at the same instant it starts. We may be arriving quite late, connecting to a planet that has been alive, steady, and developing long before our own world cooled sufficiently to sustain the first microbes. The universe may not be awaiting us to uncover life. Life may have been awaiting us to finally observe. What if the biosignatures identified by Webb do not signify an early or growing biosphere, but an advanced one, a mechanism that has already attained equilibrium between life, atmosphere, and ocean? On Earth, we are still ascending toward that condition, endlessly unsettled by geological and astronomical pressures. K2-18b may have attained it ages ago. A completed biosphere does not expand explosively. It sustains itself. It recycles effectively. It squanders little. The atmospheric chemistry seen could be the consistent yield of such a mechanism operating fluidly for millions or billions of years. If that is true, then what we are observing is not life in change, but life in equilibrium. A planet that has already resolved the issue of enduring habitability. The ramifications are astounding. We may not be uncovering life as it starts, but life as it settles into endurance. For most of human history, the universe seemed immense, cold, and quiet. Even after exoplanets were uncovered, life still appeared hypothetical, remote, provisional. K2-18b alters the emotional feel of the cosmos. Space no longer seems vacant between stars. It seems inhabited, organized, alive in spots we never considered searching. The span of 120 light years no longer feels separating. It feels close, near enough for chemistry to touch us in the shape of photons bearing biological imprints. Near enough that life elsewhere is no longer theoretical. It is quantifiable, measurable, identifiable. The universe has not abruptly become alive due to this finding. It always was. What has shifted is our capacity to perceive it. And once you pass that boundary, once you acknowledge that living worlds may be prevalent, steady, and ancient, the cosmos can never appear the same again. What the James Webb Space Telescope has disclosed is not just a planet, and not just the chance of life, but a full redefinition of our role in the universe. K2-18b is not a delicate test teetering on survival's brink. It is a steady, lasting world where life seems woven into the planet's very structure itself. Its atmosphere is not quiet. It is lively. Its chemistry is not haphazard. It is controlled. Its oceans are not fleeting. They are enduring. Everything about this world directs to one inescapable concept. Life did not struggle to persist there. It established itself, gripped firmly, and remolded the planet around it. For generations, humanity gazed outward and pondered if we were solitary, scanning the cosmos for a pale blue speck that resembled home. What we located instead was something far more disturbing and far more deep. A world that does not resemble Earth, yet maybe even better adapted for life. A prompt that nature does not require familiarity to form living mechanisms. It requires stability, chemistry, and time. And the universe possesses an abundance of all three. This instant signifies a pivotal shift. We are no longer hunting in the gloom, wishing for clues and likelihoods. We are examining the atmospheres of remote worlds and observing biology declare itself across interstellar space. K2-18b informs us that life is not a cosmic mishap, but a result. That when conditions permit, the universe does not waver to fill them with living mechanisms that endure, develop, and persist. If this finding altered how you view the night sky, Be sure to like this video, subscribe to the channel, and share it with anyone who still thinks the universe is vacant. Because from this instant onward, every star you gaze at poses a fresh query. Not whether life persists out there, but how much of it is already awaiting discovery. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.